Shall I start? Yeah, so this is a repeat of last in-house talk. So we want to predict traces using neural networks in ocean. Rajeshri has already given you the prerequisites for it, which is already very less. Traces can be thought of things like salinity in the ocean, heat in the ocean, or dissolved carbon. They are important because 80% of all the human activity heat produced is actually absorbed by the oceans. Same phytoplanktons in the oceans, for example, absorb about 50% of the carbon emission that we do. So it is important to study tracers in oceans. What do we know about the relation between the flow in the ocean and the tracer in the ocean? This picture on the right, figure 2, is actually figure 1 rotated by 90 degrees. I could have actually rotated it, but never mind. The logo would be turned around, so it doesn't matter. So we can see that these coherent structures correspond to these coherent structures, and for example, this corresponds to this. So there is a relation which we find in our observations, that if we look at the ocean flow, this is the flow, we can make some prediction about this is the heat, for instance. And what do we know about the ocean's flow themselves? This is the flow at 10 kilometers. If you are flying in a plane from very high and you take a photo, this is the type of photo you'll get. But if you are too close, like 1 kilometers away, you're probably not flying on a plane, I mean, nevertheless. This is the type of more turbulent flow that we'll see. So there is a change in, when we zoom in, the nature of basically the physics of flow really changes. What do we know about the models that model these oceans at various scales? At the larger scale, say above 100 to 1000 kilometers, that we call mesoscale, there are these quasi-geostrophic theories plus other theories that match the theory of actual ocean. So if we take, this is the energy spectrum of the actual ocean, this wiggly graph, and these dotted smooth lines are curves are the prediction of these using some Garrett-Monk theory. So we see that at large scale, we have some understanding of the ocean. But the moment we zoom in, some of these theories seem to predict something ridiculous, while the flow actual prediction of various spectrums, it is irrelevant what quantity these are. But the point is that theories do not match our observations when we zoom into the ocean. So like a simple person, I see that there is resemblance in the flow to the tracer. The only thing I can think of is apply a neural network to it. So the purpose here is apply a neural network, make it look at the vorticity, predict the tracer field. So we can see here that this coherent structure corresponds to this very nice coherent structure in the tracer. By passive tracer, we mean that it does not impact the ocean back. For example, phytoplankton is not a passive tracer, it impacts the ocean back. Carbon is, to a certain extent, a passive tracer. Okay. So yeah. There are certain type of architectures that we have used. One of them is a novel architecture where we developed a neural network layer called low conv layer. It replicates the idea of a convolution layer with some changes. I'll talk about the architectures later on. First, let us look at the results and some conclusions. Yeah. So let us look at this result. This is our model, the low conv prediction, the model that uses this low conv layer, a novel neural network layer. This is the ground truth, and this is the predicted tracer. I say that it is pretty cool, isn't it? You have very small scale predictions, very well done. A little bit diffusivity I can see here, but otherwise it's like very nice. Let us compare it with some typical So this is a unit. This is a generative adversarial neural network. This is a small autoencoder. So we see that these are the state-of-the-art image generators. At least these are components of the image generators. For example, the Ghibli images you might, instead of vorticity, you put in your photos, and instead of tracer, they produce a Ghibli image. So they use all of these adversarial techniques and unit techniques and diffusion techniques, which I have not compared to. And this is the low conf prediction, our model. You can see that this unit comes second after low conf, but at the small scales, we can see it's significantly better than all the other models. And one interesting thing about this picture is that the L1 difference between ground truth and unit compared to the ground truth and the low conf model is also almost comparable. So basically what is happening is that it is actually producing very small scale structures, but I don't have explanation. I can only say turbulence is complicated, that it acts something like a noise, and producing more turbulent small scale structures actually adds to the error. So actually this, the unit almost has same amount of error as the low conf. So is really producing small scale features important? So let us look at. So as you can see here, this red line is a unit. This orange line is a low conf. At some of the models, these are all the x-axis are different models. Some of the models actually have very comparable error with the unit. So why are the producing small scales very important? Because if we derive other components, other relevant components in our in physical systems, for example, the flux in physical space, we see that the unit which had almost the same error as our low conf produces ridiculously bad derivations of flux, whereas low conf is very much similar. Of course, there's some differences. So it is actually justified to have more small scale structure at the expense of error. Of course, these are the energy, the variance spectra of the tracers. We can see that, let's do clumsy. Yeah, we also applied it and found out regions where a lot of energy in the ocean is contained. So these are regions where 90% of the flux of the tracer is contained. So this is a nice application of our model, the low conf model. So let me talk a bit about the architectures and the novel things that we have done. So this is the basic structure of a unit, and this can be composed with other techniques like adversarial training and whatever we like, to produce various diffusion models or generative adversarial networks. So here is the unit. This is the unit. Input goes in, some skip connection, some nonsense we don't care about. What we have added is these two low conf layers. What low conf layer does is this. So a convolutional layer, first let's talk about a convolutional layer, then a low conf layer. So a convolutional layer runs small windows which tries to capture patterns in an image. The image can have multiple channels, and each of these windows extracts some features and activate them whether or not. Is it including questions? Okay. So these are the feature maps. They are activated whenever certain pattern is found and not activated when certain patterns are not found. And these weights are homogeneous across the image. So wherever you have a picture of a nice puppy, irrespective of where in the image it is, you can segment it out. But in oceans, we have a lot of non-homogeneous things. There can be continents, there can be various long-term streams, Gulf Stream, blah, blah, blah. And that can give some inhomogeneity in the oceans as we see in our planet. So what low conf does is it allows this window to change, the parameters to change, learnable parameters to change as we move in space. This is the basic thing that this low conv layer does. And this, as we saw, gives a significant improvement in the small scales. One more interesting thing that we did was with the loss function, with the loss function. Generally, you would like to predict, make a prediction so that the L1 norm or the L2 norm between the target and your prediction is reduced. This is the, so that is what is represented in loss model. It is generally the L1 norm. I have not talked about the adversarial network, which has slightly different thing. We have added one more loss, which ensures that in the inertial range of our spectrum, the target and the prediction do match. It incentivizes good prediction in our inertial range. And this again has added to a nice small scale prediction. So that's that. Basically, we are successfully producing predictions of tracer at very small scale, and we have developed a new neural network layer which might also be useful to other works where there is inhomogeneity in the processes across space.
You made a statement about this having more error than the UNet one. Why? In the previous thing, I think.
Yeah.
Yeah. Here, even like you see that smaller scale things are getting better in low conv, but the error, the L1 error in this is higher. You said like comparable but higher.
Almost equal. Yeah.
Yeah. But in the next image, next slide, when you're mapping the flux, yeah. Shouldn't you I mean, if locon was really predicting a good result for the flux compared to UNet, like remarkably different, shouldn't you define the error using this?
We could. It's hard to give a good. So, of course, my first priority will be to have a lower L1 error.
Okay.
It's not like if my flux is best produced while some very large scale components are weirdly mapped, because this flux comes with a filter at this wave number, how much from larger scale is being transferred to a smaller scale. That's what we mean by flux here, by the way.
Yeah.
So,
I'm just saying that this should be incorporated in defining which is the better.
Yes, this can be incorporated, but we have something different, which is incorporating the spectrum, which automatically helps in the flux. This so we could also do this. Basically, this is a trend that if we want to justify something is good, and the justification is using a certain metric, just keep adding all of those metric into your loss function, and all those metrics will have good list loss. But at some point, we wanted to we really don't know what are the real contributing factors to modeling good turbulence.
Okay.
If you have a non-deterministic system, for example, if you're modeling large-scale turbulence, that's...
Can you be louder?
If you have some non-deterministic system, for example, if you have some large-scale turbulence, you would add some stochastic forcing and such. So every time you do the, for example, tracer dispersion, for a run where large-scale structure are more or less the same, but because of the stochasticity, small-scale structure will change every time.
Yes.
So, but then if you try to generate a prediction of the small-scale structure, then like you should not try to 100% match the small-scale thing. So how do you make sure that your system is deterministic from what I understand? Does it?
Yes.
So if I were to try to extend this to a somewhat non-deterministic system, how will I make sure that I'm not overfitting to the...
Yes, first of all, it is hard to overfit a non-deterministic system because every run of the system gives very different results. And second, all of these networks, we feed in this vorticity. The technique is to convert this into a Bayesian learning system where along with this, the inputs that we intend, we input a set of prior, which are sampled from some normal distribution. And since they are random, the prediction will again produce random, like random small scale structures or whatever randomness actual data has. And that will be governed by this, the parameter space, maybe.
I see. So it's just that you won't be able to reduce the error beyond a point.
So
but,
there are other metrics. For example, there is something called variational lower bound error, which is often used to produce, for example, if you input the same prompt, you would like at different times to produce different results. If you put a prompt, I put a prompt, ChatGPT should produce something different. So to do that, you put the noise randomness in the parameters works, and the metric that we use is variational lower bound. That allows us to, that overcomes that thing.
I see. I have one other question. I have asked this to you before, I think, that when you talk about where the location of tracer is, how does, but you are just inputting some vorticity field and you are getting some output tracer field. But wouldn't the location of the tracers depend on, let's say, how much time has passed since the dispersion? It
Yes.
won't be a steady state thing per se.
Yeah,
So-
in our case, it is a steady state thing, because, for example, this ground truth that we have, for instance, one property of it is independent. It is, the larger scales are independent of. When I say independent, they are not really independent, but if you make different runs, you can see large correlation between the two, irrespective of the same initial condition. They only depend on the tracer field. So what phenomenon is happening here is that, so whenever you have a coherent structure here, or a bunch of coherent structures here, let's say look at all of these tracers are being trapped. And that's what our
the coherent
3D models are
structures.
also
I see.
incorporating in there.
Okay.
I just wanted a bit clarification on the low con part actually. You said that your convolution weight changes after every single stride.
Yes, horizontally, vertically, both.
Okay, so you generate like only one feature map after one convolution, is it?
Yes, you can also think of as a very small dense layers applied locally.
Okay, so I mean, don't you think like if we have like
Keep the mic in front of you.
sorry, I mean, don't you think like if we have enough number of input channel and output channel, we can still capture all these features with just normal convolution?
Of course, we can keep increasing our model size, but here the comparison in these predictions that we are doing, the unit is around 560 MB and low conv is also around 600 MB. So we want a comparable size of the models. Of course, I can just put the ultimate number of dense layers and it will capture something. But there is a problem in what you are suggesting. When my data is limited, and also basically when my data is limited, a very large model is unsuitable, because what might happen is it might get overtrained over that data, and it might get overtrained over that data, and the predictions for newer vorticities might be very biased.
Let's thank Mayank once again for such an entertaining presentation.